curated to serve as a platform for sharing knowledge, fostering collaborations, and promoting an understanding of the techniques and applications of cryo-EM. In our virtual gathering today, we transcend geographical boundaries to connect with experts, researchers, and huge people who are interested in learning these beautiful techniques from their diverse backgrounds. Throughout this series, distinguished speakers from the various institutions will guide us through the principles, methodologies, and recent developments in the cryo-electron microscopy. Their expertise and experiences promise to illuminate the path for all of us, especially to those who are just beginning their exploration in this fascinating field. I encourage each of you to actively participate, engage in the discussions, and take full advantage of this virtual networking opportunities provided by this platform. I extend my heartfelt appreciation to the organizing committees of both NIT Warangal and Shastra for this series. I especially want to thank the director of NIT, the head of Department of Biotechnology, and Professor Vignesh Ramakrishnan from Shastra, Professor Thamodaran from Shastra for making this seminar series possible, actually. As we embark on this virtual journey into the realm of cryo-electron microscopy, let us embrace opportunities it presents for learning, collaboration, and innovation. Okay, so may this seminar series contribute significantly to the advancement of cryo-EM and inspire future breakthroughs in the scientific research. So thank you all, and I wish you all a fruitful and enriching experience throughout the seminar series on Introduction to Cryo-Electron Microscopy. We have our guest with us, Professor Natesh Ramanathan. Sir, you are with us? He has joined at this one. Actually, I just managed recording. Vignesh, can you start the recording actually?
I started the recording already.
Okay, you have the controls with you, right? Okay. Yes, sir is with us.
So you're muted.
So shall I start presenting?
Okay, sir. Let me introduce you actually.
Okay.
Just one thing. Okay. So thank you so much, sir. First of all, it is both an honor and privilege to introduce our distinguished first speaker of the day, Dr. Natesh Ramanathan from the Indian Institute of Science, Education and Research, Trivandrum. Dr. Ramanathan is a luminary in the field of structural biology and is a renowned scientist in the field of cryo-electron microscopy and X-ray crystallography also. Dr. Natesh Ramanathan is currently serving as an associate professor at IISER TVM, where he leads a dynamic research group which is dedicated to unraveling the mysteries of the biomolecular structures, especially the complexes of transcription regulators in the infectious diseases. And he's primarily focusing on the proteins which are from the microbacteria using the advanced structural biology techniques. With a wealth of experience and a passion for pushing the boundaries of scientific understanding, Dr. Ramanathan stands as a beacon in the scientific community. His journey into the world of cryo-EM has been marked by a series of groundbreaking discoveries and innovation methodologies. He completed his PhD from the Indian Institute of Science, Bangalore, and then he went on to become a research scientist at the University of Bath, and then he moved to the ICGB, and from there he went to IGBNC, France. He was also a fellow of HFSP. He was a fellow of Wellcome Trust. And when he wanted to come back to India, he got this DVD Ramanathan Swami fellowship, the prestigious fellowship. And then he joined as an assistant professor with IISER TVM. I'm very happy to inform you all that he is the founding president of the cryo-electron microscopy and three-dimensional image processing society of India, which he started way back in 2018. And his research has not only contributed to the fundamental understanding of biological structures at the molecular level, but also has opened a new avenues for the drug discovery. I really have to appreciate his commitment to the excellence in research and his ability to communicate complex scientific concepts with clarity and making him an inspiring figure for both the seasoned researchers and aspiring scientists. Today, we are really fortunate to have Dr. Natesh Ramanathan here to share his insights and expertise on the cryo-electron microscopy. His talk promises to be a journey into the fascinating world of structural biology, shedding light on the techniques, challenges, and exciting possibilities of cryo-EM. And I think I will just stop it here. And I wholeheartedly invite our first guest of the day to start his presentation, actually. So, sir, thank you once again very much for taking out your time to be with us to enlighten us about the fascinating field of cryo-electron microscopy. I think, yeah, I think there's other our one of the speakers also with us. Dr. Prem is also with us actually. So,
Hi everyone, Namaskara.
Namaskaram, Prem sir. Thank you so much for joining again.
Very good. Shall I start presentation?
Yes, sir, please.
Are you able to see the presentation?
Yeah, it's visible now.
Very good. Excellent. So let me start at the beginning by thanking the organizer, Professor Tageshwaran and Ramakrishnan and all the other organizers. And let me thank Professor Tageshwaran as well for a very kind introduction. I'm humbled by the introduction, and the emphasis in this presentation would be on the evolution of cryo-EM as a structural biology method from the 70s. So I will initially talk about some of the advantages and disadvantages of the method in comparison to other techniques that are available, structural biology methods. And later on, I will also talk about, highlight some of the various techniques that are present in cryo-EM, in particular structural biology. Structural biology, cryo-EM is something that can take structural biology from in vitro realm to the in vivo realm, actually. So we will, and in situ and in vivo, and the exciting future of cryo-EM as well. So I will highlight those aspects, and I will also highlight some of the fact that crystallography and cryo-EM are friends rather than foes. Okay, and to add to that flavor, I will also give some example in the methodology that takes single particle cryo-EM from the methodology right from protein preparation, sample preparation to structure determination quickly, not though extensively. And then I will take you through the early development that happened in cryo-EM and what led to the resolution revolution. And finally, I will talk about the cryo-EM in India as well. Okay. So let me get started. Um, as you can see from this graph, the protein crystallography is number of structures with the crystallography methods is in red, and number of structures by cryo-EM methods. In particular, cryo-EM is majority in the EM field, the structures that come out because they give high resolution. So EM structures are shown in yellow. You might be keen to know that there is a crossover here. You can see that and that happened in 2017. The blue one corresponds to the NMR structures in protein data bank, and the yellow one corresponds to cryo-EM in 2017. So this data is from yesterday. So as you can see, PDB, protein data bank, still dominates structures from protein crystallography with 85%. The number is the percentage is decreasing, and the percentage of cryo-EM structures, 8.36%, is slowly increasing. Last time when I saw it was 7%, now it's 8.4%, and the NMR structure is around 6.6%. Earlier it used to be 10% actually. So you can see that cryo-EM is taking over in a very pleasant way, but that is not the end of other techniques. I would like to confirm that. Okay, other techniques has its own advantage, as I will highlight in the talk. Each technique has advantage and disadvantages, so we will look at those advantages and disadvantages in the later part of the talk. Okay, through the ability to visualize protein structures and other biomolecules, the structural biology field itself has greatly enhanced our understanding of biochemical processes of life. Okay, despite it has been little trailing in overall number of structures, the cryo-EM has experienced a recent surge, extensive surge in the recent years because of the improvement in hardware as well as the software actually. So thanks to a lot of people who do gaming in the last decades actually. So because of that, a lot of improvements in speed has come, and also the versatility of image processing has increased extensively, and it has become like more of an automated method now than the manual method that used to be a decade ago actually. So cryo-EM itself can be treated in four modalities mainly. The fifth one is soft X-ray tomography, but that is also a similar kind of method like cryo-electron tomography, but only difference is it uses X-ray, soft X-rays essentially. It has become more and more popular because you can actually visualize thicker samples. Typically, a thickness for a cryo-EM sample is somewhere around less than 2000 angstroms. Okay, and that essentially points to 0.2 micron. If it is thicker than that, essentially we have to thinner the sample and then look at it in cryo-EM conditions. But however, soft cryo-electron, soft X-ray tomography can go beyond that thickness. Actually, it can go as much as 50 nanometer, actually 500 angstroms. Okay, for tomographies. Okay, and this is the specialty of soft X-ray tomography. It can be used to look at thicker samples, higher thickness samples. Cryo-ET is one type of cryo-EM. What I will be focusing here in the technique wise in this talk briefly is the single particle cryo-EM, which is the most famous one currently, which is essentially a competitor for protein crystallography. That's what people say. By the end of this talk, I would convince that there are no competitors in science. There are only collaborators in science. Okay, so cryo-EM has other methods, modalities. The other one is the 2D electron crystallography that came in earlier years, long back ago, and later on micro-ED came into existence. 2D electron crystallography is nothing but looking at 2D crystals of especially membrane proteins. So you can actually think of 2D electron crystallography as two-dimensional crystals which do not have a third dimension. And micro ED is another technique which is becoming relatively very popular in the last 4 or 5 years because of the major effort by Tamir Gonen and co-workers. And in fact, I can give a talk on that exclusively for the specialty and advantages of micro ED. So these are the images that can give you a visual treat of these techniques. Essentially, cryo-electron crystallography, 2D crystallography is one where you have 2D crystals and you do diffraction and solve the structure. One of the advantages is that you can actually image it in the image mode and as well as do the diffraction, and you can do the 3D reconstruction using the phases that you get from the images actually. The other one, if you have a three-dimensional crystals and they are very small, typically less than 1 micron size, you can actually do micro ED, micro electron diffraction. Micro ED has become even more famous in the last few years because of the improvements in cryofib. Fib is nothing but focused ion beam milling, cryofib milling. If you have crystals, in fact, 1 micron crystals may be thicker, quite thicker for electrons to penetrate. So if you want to make it thinner, so you can actually make it thinner by using cryofib, that is focused ion beam milling. You can slice out the top and bottom layer of the protein crystal, and then you can do a micro ED, which is becoming quite popular in the last few years. The one of the other exciting venue of structural biology using cryo-EM is the thought that you can solve the structure of proteins inside the cell. Okay, and that is nothing but cryo-electron tomography, as you can see here. So this is a cryo-electron tomography of a cell with all those dots showing ribosomes in red, and there are other proteins that are shown there. So essentially, you can do a molecular replacement of proteins whose data has been acquired by cryo-electron tomography using an already known model. It's like doing, those who know crystallography will know what is molecular replacement. So essentially, you can actually solve the structure of the proteins in the cell using the models that we already have actually. One of the most popular and the focus of my brief introduction to the methodology will be the asymmetric single particle cryo-EM reconstruction, or single particle cryo-EM. I call it as SP cryo-EM. Okay. So this essentially is a method that has gained a lot of popularity in the last few years because of the fact that you can actually reach atomic resolution. Now, when I say atomic resolution, if you're a crystallographer, you will think that atomic resolution is 1.2 angstroms. But in cryo-EM, atomic resolution means better than 3 angstroms. Okay. So in that context, in my talk, I will be referring this as atomic resolution better than 3 angstroms. Okay. And essentially, you can get these atomic resolution structures by using various particles in various orientation and doing a 3D reconstruction. So the fact that when you freeze the protein crystals, the fact that when you freeze the protein samples and they are in vitrified situation and you are imaging them, you will actually have noises, and you actually take advantage of similar oriented particle averaging, adding the images of similar orientation particles and improving the signal to noise ratio. By means of that, actually you can improve the signal to noise ratio. As a result, you can actually improve the resolution of the 3D reconstruction that you obtain in single particle cryo-EM. And this has been accelerated by the fact that you can actually collect data in movie mode in the last 1 decade actually. And what do you mean by this movie mode? Essentially, you capture a particle over a period of time, and they will be moving in the electron beam, which you won't see by naked eye, but you can actually quantitatively measure those movements. And when you do that, you can actually apply correction for those motion, and that's called as motion correction actually. And because of that development in motion correction and 3D reconstruction, a resolution that used to be sub-nanometer resolution like 7-8 angstrom has now become 3.5 angstrom resolution. So routinely you can actually get sub 4 angstrom resolution with single particle cryo-EM nowadays. Whether it's 200 or 300 doesn't matter. 200 and 300 are the kilovolts of the electron microscope that I am referring to. So whether it's a 200 kV electron microscope or 300 kV electron microscopes, it is the sample that governs the resolution actually. So single particle cryo-EM is very famous now, and other technique which uses the single particle cryo-EM methodologies and features and programs is the helical reconstruction. Typically, amyloid fibrils and microtubules, they all are helical in structure, and people take advantage of this helical symmetry in order to solve the helical assemblies actually. One of the single particle cryo-EM that has been very long, for more than 5 decades, people have been working on is the icosahedral viruses. The fact that they have 20-fold symmetry is a very big advantage for single particle cryo-EM. So at the time where asymmetric particles could not go better than 8 or 9 angstrom resolution, virus particles, however, used to regularly get to 4 angstrom and 3 angstrom, and that was the kindling feature for the early dwellers of cryo-EM to improve the technique actually. Okay, so this is highlighted in Helen Seibel's review article from 2017. And if we consider these modalities, what are the advantages of these modalities and what are the challenges of each and every modality that just now we looked at actually. So the tomography itself is typically uh, a method where we lose a lot of resolution because of the fact that you have to twill the specimen, and that leads to reduction in resolution. But however, the advancement in technology have led from 20 angstrom tomography reconstructions to sub-nanometer resolution in the present days actually. In fact, there are tomographies where you can actually do sub-tomogram averaging and bring up the resolution from 8 9 angstrom to 2 3 4 angstrom actually. Subtomogram averaging has been becoming quite famous, like single particle cryo-EM nowadays. And the advantage of cryo-EM is that the advantage of tomography is that actually you can look at protein samples or protein structure in its native state, that is in the cell, in the cell in situ or in vivo actually. Okay. Single particle cryo-EM, on the other hand, has a limitation of size, and the size the smallest size where we can do a 3D reconstruction in single particle cryo-EM has been 40 kilodalton in the current day. Okay. When I moved to IISER TVM in the 2010, it was actually the limit was 200 kilodalton. So anything that is better than 200 or 400 kilodalton was better for cryo-EM. But now it has come down by a factor of 10 actually. You can see the way, the pace at which the single particle cryo-EM is advancing, and that's become very famous now. That's the reason. Okay. And as a result of the advantages of improvement in hardware and software development and movie processing, etc., we have been able to achieve atomic resolution in cryo-EM using single particle cryo-EM on a regular basis, whether it's 200 kV cryo-EM machine or 300 kV cryo-EM machine. People have been able to get atomic resolution structures on regular basis actually. And the advantage of 2D electron crystallography is that actually you can image the structure of protein in the lipid bilayer, for example, the membrane protein GPCRs. And disadvantage is that getting 2D crystals is notoriously difficult. Similarly, for micro ED, getting crystals is the disadvantage, whereas micro ED can take advantage of the fact that you can get diffraction to high resolution, and small crystals can give better resolution and higher diffraction spots. As a result, you get higher resolution structures. These are the advantages, and the references are there for you to read a little bit in more depth if you are interested. Having talked about cryo-EM and tomography, we should not forget the Indian contribution to this field, though it was done in 1970s. As you all know, in 1950s and 60s, Jane Ramachandran was very active in solving the structure of collagen. So this is a structure of Madras helix, which he and his colleague Karta solved and published in Nature paper, rubbing shoulders with Watson and Crick and Max Perutz and John Kendrew. And they are pride of our country. These structures are essentially. And the structure of collagen was a classical structure from 1954, published in Nature. Other contribution, as you all know, is the contribution of Ramachandran plot, 5-Psi map, at a time where no protein structures were known. So these are some of the contributions. PDB came into existence in 1972 or 73, for example. Okay, but these contributions were quite much earlier, but though published later on. So Ramachandran part, but many of you may not know that Ramachandran contributed indirectly to the cellular tomography reconstruction, and that is from this paper actually from 1971, the PNAS paper, three-dimensional reconstruction of radiograph and electron micrograph. Electron micrograph is nothing but electron microscopy images, and using that he was able to show that you can actually do a 3D reconstruction by Fourier transform, by convolution method instead of Fourier transform method actually. So this was at a time where G.N. Ramachandran resigned his post in Madras in 1970, and he went on a sabbatical for a year in the University of Chicago, and there he did this work, and then he subsequently moved from there to molecular biophysics unit, which many of you know in this group, especially the organizers. And before moving, he did this work on tomography. So this is something which everybody as Indians we should know. The technique, we will take the example of cryo-EM technique, and we will look at how the method is used to solve single particle cryo-EM structures of macromolecules or protein structures. So this is the micrograph of a single particle cryo-EM image. Okay, and the bottom one is actually the micrograph of the same protein with negative stain. You can see that the contrast of negative stain is quite good, but what looks very good is it need not be the very best actually. So looking is deceptive, we say, isn't it? The same is true for cryo-EM and negative stain. Negative stain looks very attractive because you can see the particle, but we lose the resolution because of the grain size of the stain that we use actually. So the grain size of the stain limits the resolution to 20 to 30 angstroms, and we can improve that a little bit to 15 angstrom, but not better than that actually. Whereas a single particle cryo-EM is free from these artifacts of heavy metal, and it can be imaged in its solution state. So it is also known as solution state structure determination, single particle cryo-EM, because we freeze the protein in solution state in space. Freezing of protein complexes in space and time, we will be able to image them under cryo conditions, under low dose conditions, and we will be able to get atomic resolution structures. And these are some of the examples. The structure on the right hand side that you are seeing here is the first structure of any protein being folded in a chaperone. So this is a GP23 protein being folded in the Groel cis chamber with capped by GP30 actually. So this is one of the first structure that were solved from our lab in 2019, where I learned cryo technique. So this is an example from my own work. I will go through the flow through of this work. So cryo itself involves 4 main steps, very similar to protein crystallography. Specimen preparation, which is essentially crystallization in protein crystallography. Here it is essentially protein purification. That's it. You don't have to do much apart from protein purification. You just take the protein sample, apply it on a grid like this. It's a EM grid, is of the order of 3 millimeter in diameter. So you apply this on the EM grid, and then you blot it and then plunge it in liquid ethane. Why liquid ethane instead of liquid nitrogen? It is because the conductivity of heat is quite fast compared to liquid nitrogen. So that's why when you fractional freeze at a very high speed from room temperature to cryo temperature of the order of minus 190 degrees centigrade, the faster is better because you will avoid formation of ice crystals, which are which are the evil of EM imaging actually, and they are the evil for proteins as well because ice crystals damage the protein structure. So the idea is to fractional freeze it at a very fast rate, and the fast rate should lead to vitrification of the water surrounding the protein. And the idea is that you have the protein in a solution state where you can actually freeze it in solution state with the surrounding as glassy material. Okay, and this essentially preserve the protein structure as well as the solvent around it actually. So that is what is shown here, plunge freezing, and then you have a section of plunge frozen sample, and this is imaged in electron microscope. Nowadays we don't use film. Earlier days the images were taken on film because it has more dynamic range. Nowadays the latest advancement in direct electron detector is almost as comparable to the film, and images that are taken, which we call it as micrographs, are essentially used for structure determination. Earlier these images were taken on film, as I said, and they used to be scanned by scanner, high resolution scanner, and from that high resolution scanner we used to get images which we used to do the 3D reconstruction. So essentially you have images of proteins which are actually cut in boxes, and you will actually align these images to references. It can be either a cylinder or any rough reference. If you have a model protein, you can use that as a reference. So you essentially align it to the references, and then you do what is known as class sums. So you can actually tell the program, there are multivariate statistical analysis program or principal component analysis, which is a statistical analysis of the set of proteins which have a particular to have a similar protein, but it can be in various orientation, and be a little bit heterogeneous also. So one of the advantages of cryo-EM is that it can handle heterogeneous sample, whereas crystallography, you need pure homogeneous protein in order to crystallize and then solve the structure. But heterogeneity is something not a problem in cryo-EM because you can actually still live with it. But the more the homogeneous, you will have more particles on the grid actually. That's the advantage. But if there is some few contamination, it doesn't matter. Or heterogeneity in the same protein is also sometimes we can use that heterogeneity to solve various structures in the same sample actually, because they have various conformations at the same time. So this heterogeneity is, you can tolerate in cryo-EM, as I will highlight the differences between protein crystallography and cryo-EM towards the end of the talk. You can actually use a set of particles that is collected, which are aligned, and then you can do analysis with those particles by what is known as principal component analysis or multivariate statistical analysis. And we will say that the most looking alike, for example, 15 to 20 images that look the most among the set can be grouped in one group. So when we do that, statistically, you can see that the signal to noise ratio of the particle increases actually. So using this, we can actually do angular reconstitution by various methods. One of the method is common lines. Nowadays, we don't worry about all these methodologies. We just go on clicking, but it's always good to know what is the underlying principle behind this methodology. What is a sinogram? What is a common line? How do two particles which are of the same protein, how do we know that how they are related by Euler angle? These are some important aspects that when you learn cryo-EM in depth, you should actually know rather than just using the graphics user interface to get the structure actually. So the technique itself, as I said, has similarity to protein crystallography. The specimen preparation, data collection, which is in this case micrograph. In crystallography, you do diffraction data collection, and structure determination using the data that you have collected. So I will show you what are the actual instruments that are involved in this. So this is the vitrification robot. We call it as WIT robot. There are many couple of companies. One is Leica, and this is the Thermo Fisher Scientific one that you are seeing here. There are new vitrification robots, Vitrojet, that are coming into the market, which boasts has better specimen preparation capabilities and better thickness control capabilities, which is done by one of the Netherlands groups. The principle is same in all this, where you actually vitrify the protein sample in solution uh, uh, by plunging the sample in liquid ethane. So this is how it is plunged into the liquid ethane. I will show you a small video of this in a few minutes time. Once it's plunge frozen, essentially the protein sample applied on the grid is actually blotted so that the thickness comes to below 2000 angstroms. And once it's plunge frozen, it is transferred into a grid holder. There are two types of grid holders. One is the side entry holder, and another one is the cassette type of holder. Essentially, you can load multiple grids in the cassette type one, but in the side entry holders, you can actually load one or maximum three. There are holders which has three positions actually here. So this is a side entry holder where you can actually load the grid onto the tip of the cryo holder. So this is a small DVAR, which is of the size of a water bottle, small water bottle, 250 ml water bottle like, and you pour liquid nitrogen into this and then maintain the tip temperature at liquid nitrogen temperatures. And we load the grid under cryo conditions under liquid nitrogen, and then this holder is inserted into the electron microscope. This is a side entry holder. The latest advancement in hardware has enabled to load several grids, up to 12 grids in a cassette, and then move that cassette into a capsule, and this capsule is directly inserted into the microscope. Okay, 200 or 300 kV microscope. So this is a multi-grid cassette where you can actually load it. Okay, so you essentially put the grid on the cartridge, and it's clipped by a C-ring actually. So essentially, when you freeze the crystal, you get frozen protein sample like this. You will see that the signal to noise ratio is very weak for a cryo frozen sample compared to a negative stain. This is actually an example from my own experiments earlier. So cryo-EM has less signal to noise ratio. In order to overcome that, as I said, we do class averages, and then we assign angles to those class averages and do a 3D reconstruction. We also separate the particles based on the homogeneity or heterogeneity, based on the heterogeneity. So we classify uh, molecules that are most looking alike into one group, so that we can call it as class 1, and second group as class 2. So there may be several classes which are homogeneous particles. Okay, so what is the advantage of this? The advantage of this is that if you have a heterogeneous sample, like in this case where we actually want to look at GROEL bound to a non-native protein, there may be several GROELs that is bound to the non-native protein, but there may be other GROELs that may not be bound to the substrate protein. Okay, in this case we have actually done the experiment to look at GROEL with Rubisco bound to it. So our interest was to look at a non-native protein. You know non-native protein, isn't it? It is a protein that is not folded actually, and they need chaperones like GROEL to help gain its structure. So we wanted to look at those non-native proteins which are essentially heterogeneous. They do not have very rigid structure. There may be some reminiscent of molten globule state, but they are not completely folded. So we wanted to look at the non-native protein in the active site. We cannot say active site, in the site where it binds to the GROEL. So taking advantage of the fact that these proteins bind to the GROEL, we were able to look at substrate proteins that were less than 200 kilodaltons. Okay, so our aim was to capture the Rubisco bound to GROEL. So this is a a reconstruction from the preliminary reconstruction from the data that was collected, and which was actually classified into occupied and unoccupied. So this is called as heterogeneity. You will have some particles with occupied groyal occupied rubisco. There will be some other particles which without substrate bound groyal. So this is essentially so if you see this movie, you will have a rubisco bound to it, so it is empty in the other side, but in the cis chamber it is rubisco bound to it, whereas in this reconstruction you see that both the sides there is no substrate bound. So actually you can separate this heterogeneity through image processing method using multivariate statistical analysis. Okay, and that is the advantage of cryo. It can handle heterogeneous sample. So by classifying such heterogeneity, we were able to get 3 different classes. 2 classes had the substrate bound rubisco. You can see that the rubisco is bound here. The third class was an empty class, which is apogroyal, and that we were able to visualize in 3 dimensions, that the rubisco binds to one of the ring, and it has native like feature, though it is not a folded functional protein. It has native like feature when it is bound to the groyal, and it has 2 domains. This is a timbarrel domain, and this is the other small domain. Okay, so that is the advantage of cryo-EM. So you can actually do a 3D reconstruction and get atomic resolution structures by image processing and 3D reconstruction methods. So this is actually sub nanometer resolution from the work that I did earlier. So that is the substrate protein rubisco bound to the groyal. So now I have highlighted the technique of cryo-EM through an example from my own experience. We will now look at how the cryo-EM that was developed in early 70s and 80s, cryo methodology, became so popular in the past 1 decade. Okay, so this is a little bit historical perspective of cryo as seen through me actually. So I started cryo in 2007 when I went to Birkbeck as a Wellcome Trust Fellow, and there I started learning cryo. So now, at that time, I was well experienced protein crystallography person, where we used to look at protein structures using the classical crystallography method: crystallization, data collection, structure determination. And that was the best method at that time. Cryo-EM was called as blobology actually. So people were not much interested in cryo-EM. But there were 3 people who were pursuing this field. They were also crystallographers, Richard Anderson, for example. But they were believing that cryo-EM can lead to some important discoveries that crystallography cannot do. And that was the belief that they stuck on, and that has rewarded them. From 1970s, 80s, they were stuck to that belief, and they were rewarded in 2017 Nobel Prize actually. So this is a journey of my own experience in cryo-EM. So 2007, when I joined Birkbeck to learn cryo-EM, the field was blobology. So all the protein structures were around 10 angstroms or worse than that, and essentially people were unable to see secondary structures at that time. 2007 was the time. And once I learned cryo-EM, so you might ask, why did I learn when this resolution was less? So there was a distinct advantage of working on larger macromolecular assemblies using cryo-EM, though the resolution was less. Okay, and that was the driving force for me to learn cryo-EM actually. And that led me to understand the nitty-gritties of cryo-EM. What are the advantages? What are the disadvantages? One of the biggest advantage, though it was low resolution than crystallography at that time, was I can look at protein complexes that were difficult to crystallize. When you have more protein complexes, it's difficult to crystallize. As you know from the history of ribosome structures, it took several decades to get the ribosome structures. And for our own example from India as well, a lot of virus structures and lectin structures. Prem would vouch for it actually. So these are the early trenders who actually believed in certain aspects of the advantages of each and every technique. So they were complementary at that time. Actually, even now, I would vouch for complementarity of each technique because each technique has its own advantage and disadvantage. So in 2007, it was a blobology, but when I moved to IISER TVM in 2010, it was still a blobology field, and the minimum size was around 400 kilodalton at that time to look at protein structure using cryo-EM. Okay, and routinely you were getting sub-nanometer resolution like 8-9 angstrom resolution for cryo-EM structures at that time. When 2013-14 came, a lot of developments happened in hardware, especially the time where you might remember that CCD cameras were replaced by CMOS cameras, actually. And that was the time where direct electron detectors were invented. And we have seen the evolution of mobiles, actually. So this evolution of mobile can be traced as evolution of cryo-EM as well, actually, truly speaking. So this technology developed because of the fact that there were direct electron detectors, and thus direct electron detectors can image protein samples as a movie. So movie processing became a very big thing. As a result of that, in 2013, the resolution improved from 12, 11, 10 angstrom to 6 angstroms drastically. Okay, I would not say movie processing. I would say improvement in hardware from tungsten filament to field emission gun machine. Okay, so that was one of the hardware development that led to bring the resolution to 6 angstrom. Then the movie processing came into existence, and that led to 6 angstroms to 3.5 angstroms or close to 3 angstrom resolution. So that was happening around 2012 to 2014, actually. So as a result of those development, many things revolutionized in single particle cryo. So the field came in from cold only during that period. Actually, it was a golden period for cryo. 2016 is my experience. As I said, these are the years that I am talking about my experience. 2016 is the time when I was in India, and there was very less facility of cryo in India. There were no direct electron detectors till 2018. So 2016 was the time where we decided, and I, Manideepa, and Vinod was in UK still at the time. We conducted the first cryo course in India, actually. And later on in 2022, 2022, 23, I don't remember why I have put this year here now, but yeah. So there were developments of atomic resolution structure in 2022-23. So you can actually get structures of proteins using cryo-EM at 1.2 angstrom resolution. So this was the time where that resolution barriers were broken several times, actually. So this is essentially the progress of the cryo-EM field shown in diagrammatic representation, and you can see the revolution has really impacted the structural biology field. And this was all possible because of the development that happened in 2000. That happened in 1970s and 80s by these three great gentlemen, Jacques Dubochet, Joachim Frank, and Richard Anderson. Jacques Dubochet was responsible for bringing the protein sample into the microscope under solution state by developing the vitrification method. Joachim Frank was responsible for developing the algorithms. He did the first program, Spider, which was used to do 3D reconstruction, and Richard Henderson was the first to show that you can actually solve structures at atomic resolution using cryo-EM. And how did this happen? We will see that in the next 10 minutes or so. So as you know, 2017, they got the Nobel Prize for high resolution structure determination of biomolecules. Okay. So let's go to some of the early days of electron microscopy and cryo-EM. Electron microscopy was discovered in 1930s. Many know that electron microscopy was discovered by Ernst Reska, which is a vertical microscope. and this was done in Kolkata by N.N. Dasgupta. Professor N.N. Dasgupta was the one who developed a horizontal electron microscope. If anybody is from Kolkata or go to Kolkata, you should visit that place where this is kept as a display monument. So this particular electron microscope field itself came into existence because of this Ernst Ruska in 1930s when he developed this vertical microscope. The resolution at that time was 1000 angstroms, which was comparable to 2000 angstrom of the modern light microscope. Okay, so whereas the current electron microscope resolution is 0.05 nanometer or 0.5 angstroms. Okay, so that is the importance of the electron microscope. Now coming to the technique per se, you actually shine electrons in the electron microscope on specimen. In the modern day, the specimen is usually vitrified, and then you take actually image. It's like taking a selfie image photograph. Only difference here is it's like X-ray imaging actually. So it is a transmission electron imaging, and then you get the image, and using that image you do a 3D reconstruction. This was having a lot of problem in 1970s because earlier days most of the EM methodology was by material science people, and material science people believed that higher dose or higher voltage electrons can essentially burn the sample. So they believed that biological specimens cannot be imaged by electron microscope. Only dead cells and dead organisms can be imaged because they will damage the specimen. Okay, but there was some development which were done by dead cells and dead organelles they were imaging, and that development led to cell biology actually, the organelle cell biology. So subcellular organelles were discovered using those methodology at the earlier days, but it was morely of dead cells and dead organelles actually. And that also led to visualizing viruses because the technology was beyond the capability of optical microscope. Electron microscope was a very big boon, though they were imaging dead cells and dead things, but people started believing that it was not, they were not able to look at live proteins or live samples. But now we know that it is possible, although it is in frozen state, we can look at them in principle, which are alive essentially. So power of electron beam would destroy biological materials. That's what they believed. And water and EM are enemies essentially. You cannot bring a protein sample or a protein in solution into the microscope because the microscope column is a vacuum, and the vacuum will burst the sample, and you don't have any more sample to image there. So that was the big disadvantage. And Jacques Duporchet was the first person who believed that you can overcome this problem by vitrification, and that led to his discovery and Nobel Prize for him, along with the other two. So as I said, other techniques are protein crystallography, NMR technique. Protein crystallography, you can get atomic resolution structures. Cryo-EM is catching up with it, though not as much as, but each technique has advantage and disadvantage. NMR is another technique where you can get ensemble structures of proteins, though they are limited by sizes. Only smallish proteins can be solved by NMR methodology. So in fact, a lot of Nobel Prizes have gone to protein crystallography and NMR structures. So why do we need another method? Okay, the main aim of another method is that even the most decorated, I will say I am the best in protein crystallography, so protein crystallography is the best. And somebody who is a cryo-EM expert who doesn't have protein crystallography, he'll say cryo-EM is the best. But each and every method has its own advantage and disadvantage. One who knows the advantage and disadvantage is the best person to tackle the research problem. So it is essentially research problem driven methodologies. Okay, so proteins that are smaller than 40 kilodalton, it's still crystallography is a big powerful method. Proteins that are smaller can be tackled by cryo-EM by using a complex with other interacting partners. So people are trying to improvise on that aspect. A lot of nanobodies are discovered which can help to solve structures of smaller proteins using a bigger protein as a binding partner. NMR is actually advantage for smaller proteins less than 20-30 kilodaltons. So that is the advantage. So cryo-EM gets around this problem, and it came up in a very big way to overcome the taboo that was existing, that it is used for only imaging dead matters. Okay, and it was thought that hitting biomolecules with electron beam can damage and destroy the protein samples. Now you know that you can actually image biomolecules without damaging. Of course, if you give a lot of more electrons doses, if electron dose is very high, it will damage. So we do imaging at low dose methodologies. Okay. So as I said, vacuum is a big problem for cryo-EM. One of the challenges of cryo-EM is that we have to use the biological sample in the vacuum, and vacuum is dangerous, and electrons is not a simple probe. It is actually a very invasive probe. Actually, it's like bombing on the protein sample when you pass electrons through it. Actually, so we have to reduce the dose to a very big extent. So we do at 10 electrons per angstrom square per second. That is the dose that it can withstand. So that is called low dose. We have to minimize the artifact of movement and artifact of electrons that are being shined on the samples. And while doing that, we have to actually see something. So because if the thickness is too much, we won't be able to see the particle or the particle of interest. If the thickness is too thin, you will not have the particles on the grid. So we want to see actually in the image something. So these are the disadvantages or challenges that we have to overcome. And we also have to image samples that maybe are moving, because electrons have charges on it. It may move the sample on the grid. Okay, so we have to look at that, and thus those challenges were overcome by image processing and movie processing, movie imaging methodologies. Okay, so thanks to cryo-EM, it has overcome all this problem, and we don't have to sacrifice resolution in these situations. So in the next 5 minutes, I will take you briefly through the history of cryo-EM. So cryo-EM, first unstained protein structure was the structure of bacteriorhodopsin at 7 angstrom, and it was happened in 1975. At that time, vitrification was not discovered actually. So Richard Henderson and Nigel Unwin were the pioneers in doing the 3D reconstruction of bacterial rhodopsin. And later on, Richard sent his colleague to Jackie Dubochet lab. They learned vitrification method. See the power of collaboration. They learned the vitrification method. They came back and then did the vitrification in MRCLMB Cambridge, and they were able to solve the structure of the same bacterial rhodopsin to 3.5 angstrom, and that was a JMB paper in 1990. So it took nearly 15 years to get that structure of cryo-EM from the unstained sample structure. Okay, so people have to wait for years. Research doesn't happen over a day or month, so it has to happen over a long period, and discoveries lead to breakthroughs actually. Okay, Jackie Dubochet, as I said, developed the vitrification method. So this vitrification method is nothing but plunge freezing the protein sample in liquid ethane and vitrifying the protein and imaging that. So we have developed a vitrifier. This was actually made from the lathe in the local lathe shop in Trivandrum. So this is a manual plunger which can be made very cheap, less than 50,000 rupees actually. So by shining electrons on the particles, we get actually the images like X-ray images. So this is the transmission electron image or micrograph, and these particles can be used to solve the structure. It's like taking a photograph, though it's a projection image of the sample, and those photographs are used to do the 3D reconstruction. There are two methods of making the particles. One is negative stain here. So this is a way in which you add a negative stain sample on the protein sample, and then you blot it, and the protein sample is is stained with negatively stained and dye, and as a result we look at positions where it is hollow, so you form a metal cast. I'm sure some of the later speakers will dwell upon this technique in more detail, but I will not get into the details of this. So that was the development of Jacques Dubochet, specimen preparation. Joachim Frank discovered the three-dimensional image processing methodologies. So he developed a computer program called Spider, and he was the first person to show that you can actually use a software program to do a 3D reconstruction of the protein sample. Richard was the first person to get the atomic resolution. He believed that with just 10,000 particles of 100 kilodalton protein, we can get atomic resolution structures, which is better than 3 angstroms. Okay, and in 1995 he published this paper. At that time, people were laughing at him. We cannot go beyond 3 angstrom. How is it possible and all? So now when people laugh at somebody in scientific field, it is worth to understand more techniques rather than laughing at other people. Okay, so essentially, it was conventionally believed that you cannot get better than 3 angstrom resolution, but we know that we have structures at 2.5 angstroms and better than 3 angstroms. It all started with this relatively very unimportant protein because its structure was solved several times at atomic resolution using crystallography. So the protein was called beta galactosidase, but now it's a superhero of cryo-EM. Actually, everybody who starts cryo-EM will start doing 3D reconstruction with this protein actually. So in a tutorial they learn how to do a 3D reconstruction of beta galactosidase. So it became a superhero because of cryo-EM actually, a simple protein. And later on, Brigade's group solved the structure of 20s proteasome at 2.8 angstrom. So you can see that these are all the structures below 3 angstrom. So they are all atomic resolution structures. And as I said, Sriram group himself broke his record of 2.5 angstroms by using the same protein to 2.2 angstrom. Why 2.2 angstrom is so important? Because you can actually start seeing protein drug interaction. Okay, drug molecules, protein water molecules interaction at this resolution. So resolution revolution became a big thing in 2012-13 because of this developments. Okay, now I'll have to go quickly. I have another 3 minutes, isn't it?
No, sir. If you want to continue, you can continue for some more time. No issues.
Okay, thanks a lot. Okay,
Thank you.
good. Okay, good. So this is essentially a movie which I will show you which essentially takes you through all the steps. So this is a movie that takes you through all the steps, which is made by Sriram. So you apply the protein sample on the grid, and then you blot it to reduce the thickness to less than 2000 angstrom approximately, and then the thin layer is vitrified in solution. So you plunge it in liquid ethane, and it is frozen in space and time. This vitrified grid is actually inserted into the modern day cassettes, and it's loaded into the capsule and loaded into the microscope. Typically a 200 kV or kilovolts or 300 kilovolt microscope, and you do imaging. This is the transmission electron microscope image, and you cut those particles and do a 3D reconstruction by image processing. So this is the overall 3D reconstruction procedure for single particle cryo-EM. Imaging for tomography is essentially done by tilting the same cells sample by plus 70 and minus 70, and you do a 3D reconstruction with those tilt images actually. So this became a big hit from 2012 to 2015, everybody started putting this is the method of the year. Nature put it as method of the year, and revolution will not be crystallized. So many articles came up, and Sriram was unstoppable. So he further went ahead and got the structure of lactate dehydrogenase at 1.8 angstrom. It's now sub 2 angstrom resolution. It's like very high resolution in crystallography actually. So there he was able to look at protein water molecules, and also for the first time he looked at protein drug interaction studies. In this case, he got the structure of beta galactosidase with PETG ligand bound to it actually. So you see that structure based drug design was having a new era using cryo-EM, and cryo-EM has advantage because you don't have to crystallize. So without crystals, you can actually get structures with a high resolution or atomic resolution. So this is the electron microscopy EM electron potential map. Cryo-EM is an electron potential map. Crystallography is an electron density map. Okay, so here it is an electron potential map, and that is the resolution that you get from cryo-EM, and you can compare that with crystallography. So I'll just show you a crystallography map. So this is a crystallography map of 0.89 angstrom from my own work at IISc in Bangalore. So you can get blobology. So cryo-EM is heading towards this. Here, blob is actually atomic resolution or ultra high resolution. So 0.89 is ultra high resolution map. So cryo-EM is heading towards that. Although it has not reached ultra high resolution yet, ultra high resolution is anything better than 0.9 angstroms, 0.95 angstroms. So breaking cryo-EM resolution barrier was possible, and this is highlighted in this article by Sriram and co-workers in 2016. So size barriers and resolution barrier was broken, and now you can actually use single particle cryo-EM to in structure-based drug design. So it is one of the important pipeline in pharma industries actually. Okay, so I will skip few slides because the time is up, and highlight the most important ones. So this is actually importance of cryo-EM in the latest SARS-CoV era, where they have developed temperature resistant spike molecule, which can be antigen molecule imitator. So they have mutated certain residues, and they were able to develop a spike which is stable at 60 degrees. So trimeric S protein, which is stable at 60 degrees. So people solved the structure of this using cryo-EM, and in 2020, Nature Structural Molecular Biology paper. So it has become a routine tool in preclinical structure-based drug design methodology. So you can actually solve the protein drug interactions and look at the protein active site where the drug is bound, and improvise the efficacy of the drug by modifying the organic molecular moiety that binds to the protein. And routinely we can get sub 2.5 angstrom resolution actually. So GPCR drug discovery has become possible because you can actually do a lot of GPCR structure using cryo-EM, which is little difficult to crystallize. Protein crystallography, membrane protein is little difficult compared to cryo-EM. So cryo-EM has taken a big step in GPCR structural biology, structure-based drug design. I showed this slide already, but I'll just highlight what made the resolution revolution possible using cryo-EM. It was the motivation method which Jackie Dubochet discovered, and FEG field emission gun technology that was developed compared to the Lab 6 or tungsten filament, which led to high spatial resolution and improvement in the resolution from 10 angstrom to 6 angstroms. Direct electron detectors that led to improvement in resolution from 6 angstroms to 3 angstroms, and there were intermediate discovery, which is volta faceplate, but the technology is so high image processing nowadays. Faceplate is only useful in tomography nowadays actually. Single particle almost many people do not use actually. and movie processing, which was essentially a gift from our computer games friends who developed GPUs actually. And new method of classification, which was the development by Joachim Frank and colleagues. All these things led to resolution revolution, and now we are reaping the benefit of the discoveries that was done by them in 70s and 80s and later in 2012s. So what are the future of cryo-EM? Cryo-EM solving the structure of protein in cell at 2.5 angstrom or 2 angstroms will be the ultimate aim for the future of cellular tomography. Automated beamline like synchrotron is a reality now. People are doing remote data collection like protein crystallography using cryo-EM beamlines in diamonds and ESRF. Visual proteomics cryo-electron tomography is the future. You can actually look at all the proteins in the cell under pathological situation at the same time. That is one thing, big thing that is going to happen in cryo-EM. Computational tool improvement is happening every day, and that is pushing the barriers of cryo-EM every day. And people who played important role is biologists, all the scientists, the development hardware, semiconductor physics people, and game industry who developed the GPUs. So these are the people who actually behind the scene who did the discoveries, which helped cryo-EM indirectly actually. So you might, as I said, I was a protein crystallography person. You might think why I learned cryo-EM. Cryo-EM and crystallography has advantages. Crystallography needs highly ordered crystals, but cryo-EM do not need. Now, routinely, you can get better than 4 angstrom nowadays without crystals, provided it's bigger than 50 kilodalton. And protein samples, we need almost like 3,000 times less protein samples for cryo-EM. Protein data banks, increasingly, you see that structures are being solved by cryo-EM nowadays, as I highlighted in the first slide. And almost it is impossible to do heterogeneous samples in crystallography because heterogeneous samples do not lead to crystals, whereas heterogeneous samples can be imaged and 3D reconstruction can be done. It is like solving 2-3 proteins in the same data collection, actually, protein structure. So people have also shown recently, there is a paper which shows that actually you can do the structural biology without purifying the protein. So you have the cell, you lyse the cell, you take the supernatant of that protein, apply it on the cryo-EM grid, and solve the structure. It's a beautiful way of solving protein structures without purifying. So this may be a trial method that people have done, but it has a big potential in future to do atomic resolution structures from cell directly, actually. So before I complete in the next 2 minutes, I will highlight some of the cryo-EM early developments in India. There is a small article that I had written in 2014. We conducted the first cryo-EM course in IISER TVM in 2016. This was the first CEM 3DIP, and this cryo-EM course is happening every 2 years now from the beginning. This was the photograph from 2016. Bomes there, Elena, Orlova, and you can see a lot of friends who are there. We also have established a cryo-EM society in India, which is called Cryo-Electron Microscopy Three-Dimensional Image Processing Society of India. You are welcome to visit the website and register yourself as a member. You can write to me at my email ID in the first slide, natesh@iisertvm.ac.in, for a reference if you want. And every 2 years we have been organizing this cryo-EM course. In 2016, 2018 it became an EMBO course. So 2018 we conducted in IIT Delhi. 2000 Vachu and many great people came for the Delhi cryo-EM, single particle cryo-EM hands-on workshop. And the first direct electron detector microscope in India came in 2018, not long ago, and that was in NCBS. Vinod and Ramaswamy was mainly instrumental in getting the instrument to NCBS, and later on IISc and many other places in India have got cryo facilities now. 2020, the cryo course was in IISER Kolkata and IISEV Kolkata. So this is some group photo from that, and that's a group photo with the Nobel laureate Joachim Frank, who was one of the 3 Nobel laureate in 2017, and that is from Prem. Prem will know who is this person, and you all know who is this person. So this essentially has been a 2-year activity of the cryo society. Every 2 years, EBO cryo course has been conducted. So last year it was in IISER Kolkata, IISER Pune, and next year, that is the coming year 2024, it will be in IISc Bangalore. So we are honored to have all these 3 laureates as a honorary fellow of this our society as well. So with that, I would like to thank everybody, and I would like to apologize for 10 minutes more time that I took. I'm open for questions if you have.
Okay, thank you so much, Dr. Natesh, for such an enlightening talk, actually. So your insights into crime basics were truly valuable, especially the way you just explain the relation between the Ramachandran and his relation to the development of the crime, and that was a really enlightening aspect for me also. Okay, so attendees, if you have any questions, I think this is the right time to open up. You can unmute and start asking your questions to our esteemed speaker, or you can put it in the chat box also.
Hello, sir.
Hi.
Sir, you said that for visualizing the image of that electron microscope, when we keep in a vacuum sample, the sample will destroy it. So I didn't get it how they are able to manage, like how do they made the sample survived and they took the image. That part I didn't get it.
So that is the one which got Nobel Prize. Jacques Dubourget was the person who devised a method to vitrify the protein samples in solution. So he essentially vitrified the protein sample under liquid ethane condition. So it was vitrified, and the protein samples are maintained at minus 196 degrees under liquid nitrogen temperature, and they are inserted into the microscope at that temperature. So it is essentially a glassy, strong material that is holding the protein in the vacuum actually. Okay, so that's how they were able to overcome the problem that existed in electron microscope, which is the vacuum in the column. We cannot remove the vacuum in the column because vacuum removing will lead to a lot of contaminations, and electrons, is having a dual wave like nature and particle like nature. The particle like nature makes the vacuum
Okay,
ideal
thank
situation for electrons. You got it? Okay. So that vacuum, if you want to bring the protein into the vacuum, it has to be vitrified. So the solution is vitrification is the answer. And that is 1/3 of the Nobel Prize, which Jacques Dubourget got it for his discovery. Very good.
Okay. So, sir, actually, I have a question. Actually, so we do have a lot of students who are in the UG, undergraduate, and some are in the PG level. They are slightly confused, like which field they have to take up. Actually. So, of course, I am trying as a structural biologist. I am trying to pull them into structural biology. So it will be really useful for them to decide their future course of action. If you can also put in some words. Out of your own journey.
Yes. So biophysics is something which is gone leaps and bounds in the last few years actually. And when you talk of structural biology, people talk of cryo-EM, okay, and nowadays, and that is because of the last decade of development in cryo-EM, and there are many challenges in cryo-EM. So if you want to be in cryo-EM field, this is the right time to get in actually. Similarly, cryo-EM is not a standalone technique actually. It's a way to understand the biological problem. So you cannot freeze yourself with cryo-EM alone. Cryo-EM is a technique which is very useful to understand the biological problem. But if you freeze yourself with cryo-EM, you can collaborate with other people in order to do many exciting frontier research areas to address biological research problems. Collaboration is a way in which you can actually tackle big complex problems. Okay, so you cannot be an expert in cryo-EM as well as an expert in mass spectroscopy. Of course, you can focus one PhD in one of the techniques. So you can do a PhD in cryo-EM and a postdoc in mass spectroscopy, but you cannot do everything in one place. Okay, so that is something that you should decide which area you are passionate about and take up the research area. So which field to choose, it's all completely subjective and depending on the research area. So if you think I want to understand protein drug interaction, then structural biology is the best way to do that actually. Okay, if you think you want to study a pathology of infectious disease, then cell biology would be a way to study that actually. So depending on what research problem that you want to address, accordingly you have to choose the technique and you try to specialize in each technique in each one of your PhD and postdoc, and if possible a second postdoc. But I would advise you all to come back to India after a postdoc before the age of 35. So that is something which you should also think, plan, and accordingly plan your area of research. Okay, cryo-EM can be learned in your one of your postdocs or a PhD time. Okay.
Okay, thank you so much, sir, for
Welcome.
explaining. There's some couple of questions I think we can take. Actually, this, yeah, okay. I think sir is also running short of time. So there's one question coming from Kinjat Mondal. So the sample is kind of carbohydrate. Where should we go with cryo or need of any modification?
If the sample is kind of carbohydrate based, not proteinaceous in nature, should we go with cryo-EM or need any modification? Carbohydrate is heterogeneous sample, so you cannot actually do single particle cryo-EM with that unless you have a proteoglycan, protein with a carbohydrate bound to it. The protein should be homogeneous in order to I mean the carbohydrate bound to it should be having same orientation with respect to protein. Then you will be able to do a 3D reconstruction with the protein along with the carbohydrate. But if you are doing only carbohydrate, it has to be cellular tomography. You can actually look at them in cellular tomography method. But since carbohydrates are not like proteins, they are not as what you say as folded like proteins, it may be difficult to visualize them in tomography that easily. So you may face a lot of challenges, and that may be something area of development itself, like carbohydrate structural biology using tomography. It will take several decades to come to that level where you can actually visualize a carbohydrate alone in a solution actually. So the best way to look at carbohydrate is NMR. Okay, so you think of heterogeneity, you can think of NMR. Okay, heterogeneity that is within capable limits, you can think of cryo-EM. Heterogeneity is there, you don't think of crystallography. Crystallography, you forget about looking at carbohydrate structures. It's impossible unless and until the carbohydrate is bound to the protein and it is ordered actually in the crystal, that is, which is very rare. It's very rare, but it is possible. I have done a lectin type of structure. I mean galactose, beta galactosidase, beta galactosyl transfer is one of the alpha GT structure with carbohydrate bound to it by crystallography. Those are very rare cases actually. So it is possible. It is not impossible, but you have to choose the right method. Okay.
Okay, sir. Yeah, thank you so much for patiently explaining and sharing
Prem.
your beautiful journey. Yeah.
Prem had a quick
Yes.
question, I think.
Yeah,
Okay.
just it's not a question. Yeah, thanks Natesh for giving so nice introduction. And it's important that audience know historically that GNR has contributed for tomography reconstruction, right? PNA is 1971. Anyway, uh, and I was thinking that annual meeting, if you announce today that other people can participate, where this time it is happening.
So the annual meeting
CEM
is going
3D.
to happen in Delhi, in your place.
Yeah, so
So-
audience get benefited.
Yeah,
they
the
can
thing is,
participate.
date is not finalized. It may be in
Okay.
January, annual meeting
Uh,
of Cryo Society. It may be in January, but we were planning to have it in 15th December. It's very short time,
okay.
but it may be postponed to January. And it
Okay,
will be in
thanks.
Delhi and it will be in IIT Delhi.
See you. You are welcome to
Very
dance
good.
here. Okay, thank you.
Excellent, excellent.
Okay. Okay, sir. Thank you so much once
Thank you very
again.
much. Thank you very much.
It's always a pleasure to listen from my seniors. Okay, that was really an enlightening talk. Actually, I really enjoyed it, and I hope all our attendees would have been already enlightened by your talk.
Thank you very much.
Okay.
Next time, I am desperate to come to
In
your
person.
place, Warangal.
Definitely, sir. Definitely, sir. It will be our pleasure to host you.
I have a good friend there, so.
Kashinath, sir. Yeah, I will convey your messages to him actually. And we also have Professor Vignesh with us.
Nice.
So, yeah, so he's from Shastra. I think he already visited Shastra sometime back.
Yes, yes.